With a wide variety of operating conditions throughout the United States, it is imperative for a trailer manufacturer to offer a broad product portfolio with equipment designed to operate efficiently in every situation. Heil Trailer International, with over 100 years of experience in the design, development, and industrialization of tank trailers, has demonstrated a core understanding of manufacturing equipment with proven performance records in the most demanding application environments. For example, the Heil petroleum trailer can be built with either a trough bottom or a double-tapered bottom. Both are effective means to unload product completely and safely, and both were developed to assure complete drainage on an incline. The perception in the market by many operators is that a double-tapered trailer drains faster than a trough-bottom trailer. This perception is not the reality, and physics shows that only height, surface area or surface friction, and the area of the outlet affect the flow rate. Lab tests on test vessels have proven this to be true. We are here at Heil Trailer International's test pad in Athens, Tennessee, where Heil's research and development team has constructed a test vessel consisting of two 2,500-gallon compartments welded together. The compartment on the left is the straight-bottom vessel with a Heil standard trough welded to the bottom and is designated the A compartment. The other compartment is the Heil tapered vessel and is designated the B compartment. Both compartments have been left uncovered, giving us a bird's-eye view during the drainage test. The procedures are straightforward. During the loading phase of the test, each compartment will be filled with approximately 2,250 gallons of water pumped through a meter to determine the exact capacity. The test will begin when we open the emergency valves on both compartments. There are two cameras covering different angles of the test. The first camera is time-sequenced and will record the loading meter and technician as water is loaded in both compartments. The second camera, mounted on a lift, will show the loading process from a position above the test vessel. During the unloading phase, one camera will be positioned to record the discharge of water out of both compartments. The second camera will record the unloading phases of the compartments from above. The test will begin simultaneously for both compartments by utilizing an air-sequenced valve that opens both emergency valves. The emergency valves are plumbed together so that they open at the exact same time. The compartments will have food coloring added to them as they fill with water during the loading phase, so it will be easier to view the flow rates during unloading. Since the medium we are using is potable water, we will simply empty the compartments on the ground. Before we begin the test, both compartments must be loaded with the same amount of liquid. The water is being pumped through a meter that allows us to measure the amount of water pumped into compartment A. As the compartment is loaded, our technician adds green household food coloring. This will allow us a better view of the flow rates of the product from above as well as from the discharge piping during the unloading phase. As the trough bottom compartment nears our target capacity, the viewer can see the predefined capacity line on the surge head. This line was defined during test trials to ensure the accuracy of the meter. The technician has signaled for the shutdown of the pump on the troughed compartment and nurses the liquid level to approximately 2,250 gallons using the meter. The technician will now zero the meter out and signal to the pump operator so he can begin filling compartment B. As the vessel fills, our technician adds red food coloring, marking the tapered compartment. Each compartment takes approximately 14 minutes to load. Once again, as the water level approaches the predefined capacity line, the technician signals shutdown of the pump and nurses the liquid level to approximately 2,250 gallons on compartment B. The compartments were loaded as accurately as possible with the pumping equipment available. For the purposes of this test, we will consider that the two compartments were loaded with the same amount of liquid. The vessel's compartments are now equally loaded and are now ready for the test. Each compartment has a typical Heil-style surge head welded in place that includes a 20-inch drain hole in the center and two 12-inch drain holes at 6 and 12 o'clock. Compartment A, the Trough compartment, has 10 3-inch diameter drain holes in the bottom of the vessel that permit the payload to drain into the 9-foot-long trough. These holes add an additional 70 square inches of area, allowing the liquid to drain to the sump and bypass the 12-inch drain hole in the bottom of the surge baffle. The trough slopes down into a 5-inch sump, the industry standard. Compartment B has a bottom that has been rolled with a taper, approximately 7 1/4 inches of drop over the length of the compartment, which corresponds to a deep drop double-tapered trailer with 13 inches of drop, which is more than twice the industry standard. The tapered compartment also has a 5-inch industry standard sump. Once the water reaches the sump on both compartments, the liquid flow is identical. Both compartments have been fitted with 5-inch by 4-inch Civicon air-operated emergency valves that will be opened simultaneously. Once opened, the water in each compartment will flow through 5-inch valves and along 6 feet of 4-inch piping to the discharge side of the test vessel. The test vessel is ready. Both compartments contain approximately 2,250 gallons of water, and it is time to open the valves. Both emergency valves open simultaneously, and the water begins to flow out of the piping at approximately 375 gallons per minute. The flow rate of a liquid is dependent upon 3 variables: the force acting on the liquid, or the liquid's height above the ground in this case, the surface area the liquid flows over, which constitutes a skin friction force acting on the water, and the area of the discharge valve and piping openings the liquid flows through. By controlling these 3 variables and ensuring each is indistinguishable between the two vessels, we ensure that neither compartment has an advantage over the other. The first variable, compartment height above the ground, is easy to control. Both compartments' bellies are 18 inches above the ground at the sump. Compartment A is a straight-bottomed troughed vessel, so its height remains consistent along the entire length of the compartment. Compartment B is a tapered vessel, and its bottom actually averages slightly higher off the ground when considering the entire length. This gives it a slight advantage over the troughed compartment due to the force of gravity. Surface area is the second variable we must control. This variable acts on a liquid in the form of friction. The more viscous or resistant to flow a liquid is, the more frictional force surface area imparts on the liquid, slowing the flow down. Fortunately, the medium we are using has a very low viscosity. Water is similar to kerosene, and only slightly more viscous than gasoline. Since the length, width, and height of the vessels are comparable, and each compartment includes a similar surge baffle, the difference in surface area is negligible between the compartments. The last variable we must control is the area of the outlet valves and discharge pipe openings. We have installed a 5-inch sump, a 5-inch by 4-inch emergency valve, and 6 feet of 4-inch piping the liquid must travel through before it exits the vessel. This ensures both compartments have similar areas the water flows through. We are near the end of the test, and it is interesting to note the damming effect the surge head has on the water in the double taper compartment. Because the water must flow through the 12-inch opening of the surge head at the 6 o'clock position, a non-laminar or turbulent flow is created which slows the final stage of drainage on that compartment. This has been labeled gurgle time by tank truck operators. Gurgle time is defined as the final seconds of product drainage that is slightly restricted by the openings in the surge heads. This restriction or damming effect is eliminated on compartments with drain troughs because the product's flow path bypasses the surge heads. The water flow remains laminar or non-turbulent as it travels through the 3-inch drain holes in the bottom of the vessel into the trough. This permits a trough compartment to actually drain slightly quicker in the final seconds of unloading. As the final drops of water empty from the vessel, it is evident that both compartments completely drained in approximately 6 minutes within 5 seconds of each other. The trough compartment actually drained slightly quicker due to the gurgle time the tapered compartment experienced. The laws of physics have remained constant, and our test has been successful. As this presentation has demonstrated, the trough bottom trailer will drain just as quickly as a double taper trailer, if not quicker, due to the damming action or gurgle time at the surge heads. If your operating environment requires you to unload on inclines and complete unloading is a concern to you, consider Heil's trough bottom trailer. It is more efficient than the double taper design, and more pitch or grade can be designed into the trough to ensure complete drainage for your operating conditions. Heil Trailer International currently has the most extensive sales, service, and repair network in the industry, ensuring you will receive superior representation and customer service throughout the life of your trailer. Give us a call and let us tell you about the complete line of Heil trailers that can be equipped to handle any of your transportation needs.